In this video, we're going to be talking about separable equations, which is another form of a first-order differential equation. So let's first start by defining it. So a separable differential equation is any equation that can be written in the form y prime equals f of x times g of y, or dy dx equals f of x times g of y. Now, what makes these equations separable is the fact that, and I'll use this one right here, is the fact that we can actually separate by grouping the variables together on each side. So like for example here, I'm going to multiply both sides of my equation by dx first. So that gives me dy equals f of x times g of y times dx. And then next, I'm going to divide both sides by g of y. So that gives me dy over g of y equals f of x dx. And from here, to solve this, what you would do is you would integrate both sides, respectively, to their variables. And then you would go ahead and solve for y, if possible. Now, what's really nice about differential equations, in fact, let me be more specific here. What's really nice about separable equations is that there's almost like a formulaic approach to them. So the big thing that we got to be able to recognize first is, do we meet the form y prime equals f of x times g of y, or dy dx equals f of x times g of y. So if you have these forms, you've got to be able to recognize, okay, that's separable. All right. So some examples of separable equations. All right, will look like this, something like y prime equals x to the second minus 4 times the quantity 3y plus 2. Another example could be dy dx equals xy plus 3x minus 2y minus 6. Even an example like this, and this is a special one, y prime equals secant y plus tangent y. And this is special because it is called an autonomous differential equation. And the reason why it's autonomous is because the right-hand side is only in the variable y. That's it. Okay? So I think, like I said, because these are very formulaic, I think I'm just going to write down like an approach. All right. So the first thing you want to do is check for any values of y that make g of y equal to 0. If you find those, these are called constant solutions, meaning they're just numbers. All right. Second, you're going to rewrite y prime equals f of x times g of y as y prime over g of y equals f of x dx. Or if you're using Leibniz notation, we could just make this dy over dx equals dy over g of y equals f of x dx. So they're the same thing. Okay? Step 3, you're going to integrate both sides of the equation Step 4. You're going to solve for y, if possible. Sometimes you can't, and that's okay. If you can solve for y, all right, that is called an explicit solution. And the if possible, or if you can't, let me write it like this in red. If we can't, this is called an implicit solution. And you should remember those terms from when you were learning derivatives in Calc 1, where you have explicit differentiation and then implicit differentiation. And then step 5, if you have initial conditions, substitute for x and y and solve for the constant. So let's see how this works. We're going to go ahead and solve y prime, which equals x to the second minus 4 times 3y plus 2. All right. Now, like I said, first thing, does this meet the criteria that it's separable? Well, you got y prime on the left. On the right-hand side, you have f of x times g of y. So this is 100% separable. All right. So what we're going to do is I'm going to rewrite this as dy dx equals x to the second minus 4 times 3y plus 2. And I'm going to go ahead and separate these variables. So we're going to multiply dx from both sides. And then divide both sides by 3y plus 2. So that gives me dy over 3y plus 2 equals the quantity x to the second minus 4 dx. All right. Now that we have them separated, we are going to integrate both sides of the equation. All right. So we'll do the easy one first. It's going to be on the right-hand side. The integral of x to the second is 1/3 x to the third. The integral of 4 would be minus 4x. And I'm going to put the plus c here for now. I'm going to write this 3 a little nicer as well. Now, on the left-hand side, that's a little bit more difficult because what we're going to have to use is u substitution. So we're going to let u equal 3y plus 2, du equals 3, dy, and then I'm just going to move the 3 over to the right-hand or left-hand side. So now when I go to integrate this, I get a 1/3 out front, 1 over u du. And then when I integrate this, I get 1/3 times the ln of u, which equals all this on the right-hand side still. And finally, we're going to go back in and substitute what u was. So we get 1/3 times the ln of the absolute value of 3y plus 2 equals 1/3 x to the third minus 4x plus c. And now what we're going to have to do is solve for y. Now our y is right there inside of the natural log. But that's easy enough. We know how to solve for that. First thing I'm going to do, I'm going to multiply everything by 3. So that's going to give me the natural log the absolute value of 3y plus 2 equals x to the third minus 12x. And I'm going to write plus c, okay? But technically, this is 3c, which some books would abbreviate this as c1. But when you think about it, 3 times a constant is another constant. So we're just going to leave it as plus c for now. All right? Now the question becomes, well, how do we solve for y? Well, you're going to go back to your properties of logs. I'm going to exponentiate using e to both sides of my equation here. All right. So that's going to give me on the left-hand side 3y plus 2. Remember your properties for logs. E to the log base e of x is equal to x. So it's the same thing here. Nothing changes there. That's a property that you would have learned back in pre-calc. And then on the right-hand side, all right, on the right-hand side, I am going to leave it like this for now. We're going to fix that in a second. All right. So here's what we are looking at. Now the question becomes, like I said, how do we fix this? Or better yet, I think let's stick to our math words. How do we simplify? Well, it's easy enough. Remember, the product rules for exponents. Remember this product rule? It says if the bases are the same, all you do is add the exponents together, right? So, going from left to right, here's what we end up getting. We get e, and I'm going to write it like this. E to the x to the third minus 12x times e to the c. Now, what I did here is I just applied this product rule right here. All right. With keeping these two the same. And then there, right here, is that plus c. So, e to the x to the third minus 12x times e to the c. Now, e to the c is a constant raised to another constant. All right? So what ends up happening here is that just becomes a big constant. We're going to call it, for now, c2. Okay? But remember, we still have this e to the x to the third minus 12x here. Okay? And going from left to right, we can go ahead and solve this. All right? Because what I'm going to do is I'm going to subtract 2 from both sides. All right? And finally, divide everything by 3. So I end up with y equals, well, let me write that cleaner. Y equals negative 2 plus c2 e to the x to the third minus 12x, all divided by 3 for a final solution. Now, there is something I do want us to go back and look at. And that's going to be all the way back up here. Here I have the absolute value of 3y plus 2 for the argument of my natural log. But then, if you notice, I kind of dropped it. And I did that because I kind of knew where this was going. But technically, you still have the absolute value there, which this is going to transition all the way down. Okay? But what ends up happening here is this. As soon as we subtract 2 from both sides, all right, we got to get rid of this absolute value symbol. So technically, this is really plus or minus C2, where C2 is equal to e to the c. All right? So the thing you're going to notice here, all right, is that Whenever you are adding two constants together, you get another constant. Whenever you are multiplying constants together, you get another constant. Whenever you have a constant raised to another constant, you get another constant. So we do not need the C2 here anymore if we just define it off to the right. And this is not the class where we're going to have to really worry about that, but I do want us to understand what's happening. When you go ahead and you take a differential equations course, then things change a little bit. Right now, we are just concerned with recognizing separable equations and then learning how to solve them. The second thing is this. Because C2 is always going to be greater than 0, because e to the c is always going to be greater than 0, no matter what. Like even if c is a negative number, like e to the negative 1, that's just 1 over e, which is still a positive number. So because c2 is always positive, I don't have to worry about the plus or minus. Like I don't have to worry about the minus part in my solution. And the reason for that is because c2 is greater than 0. All right? So our final solution here is y equals negative 2 plus c e to the x to the third minus 12x, all divided by 3. It's not exactly the prettiest answer, but this is how this works. All right? Now what I'd like to do is do another one here with initial conditions, so we can see how it flows. So once again, we're just going to solve. In this case, it's going to be an initial value problem. And it's going to be dy dx equals the quantity 2x plus 3 times y squared minus 4, where we have the initial values y of 0 equals 1. So if you wanted to, you can come over here and just say, well, this means x equals 0 and y equals negative 1. And we'll worry about that all the way at the end. So is this separable? Well, here's our dy dx. Right here is our function of x. And right here is our function of y. So we are good to go in terms of separation. So let's see if we can do this in just one step. We're going to get dy over y squared minus 4 equals the quantity 2x plus 3 times dx. Now, we're going to integrate both sides. We're going to do the easy side first, which is the right side. We end up getting the integral of x to the second plus 3x plus c. It's the left-hand side we really got to be concerned with. And the reason for that is in order to integrate the left-hand side, we're going to have to use partial fraction decomposition. Remember, I think it's a good idea to start thinking this way. And what I mean by that, and this is not me on my soapbox saying, think like me. This is just me trying to give some guidance. When you were thinking about integration, all right, the first thing you should try to do is use those basic rules, like the power rule and stuff like that. The second thing you should be thinking of is use substitution. In other words, if your basic rules do not work, maybe use substitution will work. If use substitution doesn't work, then maybe you should be thinking about integration by parts. And I'm going to write this as 3a. 3b would be trig integrals. 3c would be trig substitution. 4 would be partial fraction decomposition. I mean, all these techniques kick in. And the thing is, this is what those right there, the 3a, 3b, 3c, and 4, that's everything we learned previously. And you better believe that they're going to appear from now until we are done with this semester. So this kind of at least just gives you like, oops, sorry, didn't mean to do that. This just gives you like a little bit of, I guess, a game plan, right? So we're going to have to use a partial fraction decomposition here on the left. And I'm going to just set it up for us. So I'm going to leave my marker in green. So this is just going to be the integral of dy over the quantity y plus 2 times the quantity y minus 2. That's y squared minus 4's difference of squares. So we know this is going to end up being the integral of a over b plus b over y minus 2, because those are non-repeating linear factors. And yeah, I'll go ahead. I'll do the partial fraction decomposition for us, just so we remember how it looks. So we have 1 over the factored form equals a. Now remember, a already has the y plus 2. So this is just going to be y minus 2 plus b times, well, remember, the b already has the y minus 2. So we'll make it y plus 2. So this turns out just to be 1 equals ay minus 2a plus by plus 2b. Gives us 1 equals a plus b times y, the quantity a plus b times y, plus the quantity negative 2a plus 2b. And our system of equations will look like this. A plus b equals 0, and negative 2a plus 2b equals 1. So if you wanted to get out a matrix, you could do that here. It's totally fine. If you wanted to, you can just solve this system of equations here. What I think I'm going to do is I'm going to solve this by the addition elimination method. So if you remember, I'm going to multiply equation 1 by positive 2. That's going to give me 2a plus 2b equals 0. Then we have negative 2a plus 2b equals 1. When we add these together, these two equations together, we end up getting 4b equals 1. Therefore, b has to equal 1/4. And since we know b equals 1/4, I'll use equation 1 to solve for a, which means a equals negative 1/4. So, at the end of the day, we're going to get the integral of negative 1/4 times 1 over y plus 2 plus 1/4 times 1 over y minus 2 dy. I am going to rewrite this as 1/4 times 1 over y minus 2 minus 1/4 times 1 over y plus 2. And the reason why I did that is because I want this first term to be positive, because if you look, they both have a 1/4 in common. So I'm going to go ahead and factor out the 1/4. And then when I integrate, all I have to worry about is integrating 1 over y minus 2, which is going to be the natural log of y minus 2, minus 1 over, or the integral of 1 over y plus 2, which is just the natural log of y plus 2. And don't forget, we still have 4x to the second. Oh, I'm sorry, I'm moving too fast. X to the second plus 3x plus c. From here, I'm going to multiply everything by 4. Hence why I started writing 4x to the second about a minute ago, or a second ago. So multiplying everything by 4 gives me the natural log of y minus 2 minus the natural log of y plus 2 equals 4x to the second plus 12x plus, we're going to call it C1, where C1 equals 4c, and try to solve for this y. We're going to have to use our rules for logs, properties for logs, and when you have a minus sign, And you have the same logarithmic function out front. So we have a minus sign with the same ln's. That is just going to turn into the ln of y minus 2 over y plus 2, which equals 4x to the second plus 12x plus c1. And we're going to do the same exact thing what we did previously, which is we're going to exponentiate. We're going to raise both sides of the equation. We're going to put it to the exponent of e. So give me a second. Let me write this stuff out. We're going to keep these two the same. We're going to keep them together, and we're going to separate out that plus c1. So on the left-hand side, we end up getting the absolute value of y minus 2 over y plus 2 equals c2 e to the 4x to the second plus 12x, where c2 equals e to the c1. All right. So I hope you kind of see what's happening here. All right. I know it looks a little crazy at first, but this is just part of the solution. So now the big question becomes, we got to remove the absolute value. And when we do that, we can let C be either positive, or I'm sorry, we can let C2 either be positive or negative. So we're going to remove the absolute value and let C2 be either positive or negative. All right. So here's what we're going to do. I'm going to write y minus 2 equals C2 times the quantity y plus 2 e to the 4x to the second plus 12x. What I did is when we removed the absolute values, I multiplied both sides of my equation by the quantity, oops, I'm running out of space, by the quantity y plus 2. So that's how I got the y plus 2 over here. So now what I'm going to do here, and it's going to look a little weird at first, maybe not. I have C2, I have e to the 4x plus 12, and all I'm going to do is just distribute. Y minus 2 equals C2 times y e to the 4x to the second plus 12x plus C2 times 2 e to the 4x to the second plus 12x. Now, we're going to collect all the terms that have the variable y. I'm going to get all the y's on one side, everything else on the opposite side. So this term right here contains a y in it. This term right here does not have a y in it. Therefore, I'm just going to move them to opposite sides. So I get y minus C2 times y e to the 4x squared plus 12x equals positive 2 plus 2 C2e to the 4x squared plus 12x. And now, notice, I have the variable y and a variable y, which means I can factor it out. So there we go. I just factored it out. And finally, at the end of the day, y is going to equal 2 plus 2c2 e to the 4x to the second plus 12x, all divided by 1 minus c2 e to the 4x to the second plus 12x. We have initial conditions. So, to find the value, c2, remember, x equaled 0 and y equaled -1. All we got to do, substitute a -1 for y, and wherever we see an x, we're going to put a 0. So it's just a lot of substituting real quick. Please bear with me. All right. So it looks like we get -1 equals 2 plus, well, this right here is e to the 0 plus 0. So it's e to the 0, which is 1. So we end up getting 2c2 over 1 minus c2. And then when you go ahead and you do all your algebra and everything here, you should turn up with c2 equals -3. This video is already getting very long, so I just want to cut to the chase. All right, so y equals 2 minus 6e to the 4x to the second plus 12x all over 1 plus 3e to the 4x to the second plus 12x for our particular solution. In the next video, I'm going to go over some of the very famous applications of separation of variables. So that's going to be in another video.